Welcome to the third lecture of General Chemistry. In this lecture we're going to be talking about bonding, and this material can be found in Chapter 9 of the text. Before we start with bonding, let's do a couple of review questions from Chapter 8. Question 1. Write the full electron configuration for the second period element with the smallest size. So this tests your ability to first find the element with the smallest atomic size, and second, to write the full electron configuration. Now, if you remember, atomic size increases as you go to the left side of the periodic table and as you go down a group. So the smallest atoms are going to be on the right side of the periodic table and towards the top. So in the third period, the third row, second period, the smallest element will be neon. So now we need to write the full electron configuration for neon. So we have 1s2. So here's 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, and finally 2p6. 2p6. Okay, so that would be the full electron configuration. If you wanted to write the condensed configuration, you can just show that as simply neon with brackets because it is a noble gas and it has a filled shell. Okay, second question. Which third period element has the lowest ionization energy? In the second part, write a condensed electron configuration for this atom as a +1 ion. So if we look in the third row, which element has the lowest ionization energy? Now, if you remember, ionization energy has the opposite trend to atomic size. It increases as you go to the right and up a group. So that would mean the lowest ionization energy would be on the left side, so it would be sodium. Now if we want to write sodium's condensed electron configuration for the +1 ion, what would that be? So sodium would normally have a filled shell to neon and then one extra electron in the 3s orbital. But if we lose an electron, we lose that 3s electron, then the configuration would simply be that of neon. So we can just write it neon in brackets. Okay, on to Chapter 9. So the first part of Chapter 9, Section 9.1, we're just going to talk generally about chemical bonds. And what is a chemical bond? Well, a chemical bond is caused by electrostatic forces holding groups of atoms together. Now there are three different types or categories or flavors, if you want to think of them that way, of chemical bonds. You have covalent bonds. And these are where an electron pair is shared. You have ionic bonds, and this is where electrons are transferred from one atom to another. And finally, we have metallic bonds, which are a little bit different, a little bit hard to think about, but basically it's cations of the metal in a sea of electrons. And towards the end of class today, we'll talk a little bit about metallic bonds. So the big question is, in Chapter 8, we saw that electron configurations in atoms adopt configurations that give the lowest energy possible. So if you have these atoms and their electrons are the lowest energy possible, why do two atoms come together to form a bond? The answer to this is the same answer that many things in nature, it's the same answer for many things in nature. Bonding lowers energy. How does it do that? So here's a figure from the book. This is a potential energy curve. And these two blue dots up here are separate hydrogen atoms. So at point A, they're far enough apart that they don't notice each other. They can't feel each other. So the potential energy at this point A, is 0. As these two hydrogen atoms get closer to one another, what starts to happen is the electron cloud, the blue part, from one hydrogen atom starts to fill the attractive force of the nucleus from hydrogen atom number 2, and vice versa. The electron cloud on hydrogen atom 2 feels the attractive force from the nucleus on hydrogen atom 1. And what that does is it lowers the potential energy, because we have this attractive force. As they keep getting closer, the potential energy keeps getting lower and lower until we reach a minimum. Then if you keep getting closer from this point, the nuclei start getting close enough that they start repelling each other. And then if you follow this curve up to very close distances, it gets really, really positive. So that's a very, very strong repulsive force. Well, the deepness of this curve, of this minimum, that equals the bonding energy of those two atoms. And where that minimum occurs on the x-axis, which is distance, would be a bond length. And we'll talk a little bit more about this plot when we talk about covalent bonds specifically. We saw this periodic table, I believe, in chapter 8, but I wanted to show it again. I think it's good to have it presented again. And this is color-coded. So you see that the blue color represents metals, and they tend to be on the, if you remember from last lecture, the metals tend to be on the left side of the periodic table. The non-metals tend to be on the right side. And then we have these green metalloids that are at the transition between the two. And what are some key properties of metals and non-metals? Well, atomic size. A metal, because they are on the left side, they tend to be larger. Non-metals are smaller. The effective nuclear charge in a metal atom is lower, because again they're on the left side of the periodic table, and the effective nuclear charge in a nonmetal is higher. Ionization energy, lower for metals. Electron affinity is less negative for metals. What does that mean? That means they lose electrons easier. Nonmetals, the ionization energy is higher. Electron affinity is more negative, so they tend to gain electrons. They want to gain electrons. Metals want to lose. Non-metals want to gain electrons. So let's look a little bit more in detail about the three different flavors, if you will, of chemical bonds. So first, ionic bonds. Now this involves a transfer of electrons, and it's usually between a metal and a nonmetal. So what happens is the metal will transfer electrons to the nonmetal. The metal wants to give up electrons, the nonmetal wants to take in more electrons. And why is that? Because they both want to get to a configuration that is like a noble gas configuration. And a classic example of this would be sodium chloride, which is table salt. Second type of bonding we're going to talk about is covalent bonds. And these bonds are where the electrons are shared between two, usually nonmetals. So two nonmetals come together. Neither of them wants to give up electrons, so they both end up sharing them. An example of this would be cyanide. We have three nonmetals bonded together. And finally, metallic bonding. And this involves electron pooling, and it occurs between a metal and another metal. Now, if we look at a figure that shows this, a picture of these three different types of bonding. First, ionic bonding. You have a metal, sodium. It transfers an electron to a nonmetal, in this case chlorine. What you're left with is a sodium cation and a chlorine anion. The cation's positively charged, the anion's negatively charged, so they attract one another. For a covalent bond, you have two nonmetals that come together. In this example, it's chlorine and bromine, and they share electrons. And you see that they actually form separate, distinct molecules, where they, in contrast to the ionic substance that makes a continuous crystal lattice. And finally, we have metal bonding. In this case, we're using sodium metal. So these sort of come together, and they tend to lose that electron, that 3s electron they have, and the loose electrons sort of swim around the sodium cations. And that's one of the reasons why metal is so conductive of electricity, is because it has a pool of electrons swimming around. Right. Figure 9.3 is in your book. This is an interesting figure if you want to look at the periodic trends. It shows the third row in black type, and then column 4A in the red type. And you can see as you move across a period or up or down a row how the bonding changes. And this is a little bit probably more confusing than just looking back at last time, chapter 8, the periodic table and the trends with metallic behavior. So why do bonds form the way they do? What theory can we use to explain this? It turns out what we use to explain bonding in this general chemistry sort of level is Lewis theory. This was developed by Gilbert Lewis in 1916. And he proposed that atoms tend to lose or gain or share electrons to achieve electron configuration of a noble gas. So they tend to give up electrons or pick up electrons so that they meet the nearest noble gas configuration. And this is where the idea of the octet comes from. And if you've taken chemistry in high school, you probably remember the octet rule. And what that is a set of 8 valence electrons fills a valence shell. So when we're not considering transition metals in this case, we're just considering the main group elements. 8 electrons will fill a valence shell. You have 2 in the s orbital and 6 in the p orbital. There are some exceptions to this. Hydrogen can only have a maximum of 2 electrons because it only has the 1s orbital to fill a shell. And then also elements to the left of carbon don't necessarily follow the octet. Another important contribution Lewis made is Lewis electron dot symbols. Now, to draw a Lewis symbol for a main group element, there are 4 steps. So the first step, you write the element symbol, and this represents the nucleus and the inner shell electrons. And then you note the column, the A group that it's in, and this gives you the number of valence electrons that you have to add. So you place 1 dot at a time on each of the 4 sides of the element, and you keep adding these dots until all the electrons are used up. So if we wanted to do an a Lewis dot symbol for nitrogen, we'd write nitrogen, the N stands for nitrogen. And now, how many valence electrons does nitrogen have? Well, it's in group 5A, so there are 5 valence electrons. So then we place 1 electron, and we go around the atom until we've used up all 5. So this would be the Lewis symbol for nitrogen. Okay, and the dots on this figure are a little bit skewed, but you get the point that any of these ways of drawing it is correct. It doesn't matter where you double up the electrons, just that you have 3 electrons that are not paired, and then one set of paired electrons, giving you a total of 5 valence electrons. Okay. For a metal, the total number of dots in the Lewis symbol is the number of electrons that atom loses to form a cation. So if we draw the Lewis symbol for magnesium, it would be shown here, magnesium with 2 dots. Now magnesium is going to lose those 2 dots. It's a metal. It wants to give up electrons, and it goes to the Mg2+ cation. For a nonmetal, the number of unpaired dots equals the number of electrons the atom gains to form an anion, or the number it shares to form covalent bonds. So for fluorine, we see the Lewis symbol for fluorine. It has 7 valence electrons. Now it can gain an electron to form a negatively charged anion, fluorine minus. So there would be 8 electrons around that fluorine atom. So the octet rule states that when atoms bond, they lose, gain, or share electrons to attain a filled outer level of 8 electrons. Or in the case of hydrogen and lithium, 2 would fill their shells. So we're always trying to get filled shells. Here's a figure of the Lewis symbols from the 2nd and 3rd rows of the periodic table. And I want to point out this term. It's an important term when you're talking about Lewis symbols. The number of unpaired dots is the bonding capacity. And this is how many bonds an atom can form. So if you ever want to know why carbon compounds tend to form 4 bonds, that's why. They need 4 bonds to complete their octet. Nitrogen tends to form 3 bonds, oxygen 2, and fluorine 1. Okay, moving on to section 9.2. Now we're going to talk about ionic bonding in a little bit more detail. And first we'll start with this cartoon where all the boys in the class are cations and the girls outside are anions. And yes, they're attracted to the girls. So again, an ionic bond forms when a metal transfers electrons to a nonmetal. Now this forms ions. The metal becomes a cation, the nonmetal becomes an anion, and then they attract each other. And this gives a compound which is referred to as a salt. So when a metal and a nonmetal form a compound, they form what is known as a salt. And of course, the best example of this is what we call salt or table salt, is sodium chloride. The total number of electrons lost by the metal equals the total number of electrons gained by the nonmetal. Now, if we have an example with sodium oxide, sodium, it's in the first column, so it's going to lose 1 electron. Now, oxygen, it's in the group 6A, so it wants to gain 2 electrons, not just 1. Sodium can only give up 1 electron, but oxygen wants 2. So what does that mean? That means we have to have 2 sodium atoms for every oxygen atom if they're going to form a compound. So just to remind everyone again, an ionic bond is an electrostatic attraction, and they're very closely packed, oppositely charged ions. And a cation, if you remember, is positively charged. This is in an ionic compound, this is due to a metal losing electrons. Remember, metals have low ionization energies. And the anion is negatively charged, and this is due to elements that have high electron affinity, which, what does that mean? They're on the right-hand side of the periodic table, so they're nonmetals. There's 3 ways to depict this electron transfer in an ionic bond. And if we use the example the book gives of lithium and fluorine, you can do electron configurations. So you see that lithium has 1 electron in the 2s orbital. Fluorine has 5 electrons in the 2p orbital. If lithium gives up that 2s electron, it becomes lithium plus, and it only has 1s2 configuration. Fluorine becomes fluorine minus, and now it has a filled shell. We can also draw orbital diagrams. So here we see the orbital diagram, partial orbital diagram for lithium and for fluorine. Now lithium gives up 1 electron to fluorine, and then we're left with lithium plus and fluorine minus. And these are the new configurations. And then the way I think is probably the easiest way to show it is by Lewis symbols. So here we see lithium. It gives up 1 electron, you see with the arrow, to fluorine, and we're left with lithium plus and fluorine minus. So let's try a practice question now. Use partial orbital diagrams and Lewis symbols to depict the formation of calcium 2+ and fluorine minus ions from the atoms, and determine the formula of the ionic compound they form. Okay. So we can draw the partial orbital diagrams for both. So calcium is a 4s2. So that would be the partial orbital diagram for calcium. Fluorine, 1s2, 2s2, and 2p5. Now when they form their bond, this electron had too many electrons. Okay, this electron will move here, but you'll notice that calcium will still have one electron left. So it's going to give up that electron to another fluorine atom. And what we'll be left with would be calcium 2+ with an empty 4s orbital. And then we'll have 2 fluorines. That have completely filled valence shells. And I didn't fill that according to Hund's rule, so I'll do that. Make sure I do it this time. Okay. So that would be partial orbital diagrams. The way I think is easier to show it would be Lewis dot symbols. So that's the Lewis symbol for calcium, the Lewis symbol for fluorine. Calcium's going to give up an electron. To fluorine. But you notice fluorine can only take one. Calcium has 2 electrons to give up. So it's going to give that up another one to fluorine. Another fluorine. And what we'll be left with is 2 fluorine anions and 1 calcium 2+ cation. And from using the orbital diagrams or the Lewis symbols, we can determine the formula for this compound would be calcium difluoride. Here's another question you might be thinking. How can we predict the strength of ionic bonds? So what is the periodic trend? Well, the term lattice energy, the definition is the energy required to separate 1 mole of an ionic solid into a gaseous ions. I don't think that's as important for you to remember. It's more important just to remember the term lattice energy is the strength of an ionic bond. Should probably highlight that. And how do we determine the lattice energy? That's by Coulomb's law. And this is from Chapter 2. Chapter 2 talks a little bit about Coulomb's law. But what Coulomb's law states is the electrostatic energy is proportional to the 2 charges. So if we have A and B, to tell how attracted they are to one another, we need to know the charges on A, the charge on B, and the distance between them. So when we're talking about ionic compound, the strength of an ionic bond, we would have the cation charge multiplied by the anion charge divided by the cation radius plus the anion radius. So let's think about this. Lattice energy is affected by ionic size and ionic charge. So as ionic size increases, what does that do to lattice energy? As the ions get bigger, the distance between them gets bigger. And the distance is on the bottom of this fraction. So what does that do to the electrostatic energy? That decreases it. So the strength of an ionic bond gets smaller as the ions in that ionic bond get bigger. If you remember the periodic trend for size, size goes up when you go down a group. So lattice energy is going to decrease when you go down a group on the periodic table. As the charge increases, now if we think about charge, as charge increases, the lattice energy increases because the charges are on the top of the fraction. Now let's look at a figure that shows this sort of trend. So if we just take fluorine here, the fluorine anion, and compare the group 1 metals, how strong their bonds are when they form bonds with fluorine, we see that lithium is the strongest. And why is that? It's because it's the smallest cation. So the distance between the lithium and the fluorine is the smallest, so that bond is the strongest. And as we go down that group 1A, we see that the lattice energy, that the ionic bond strengths keep getting lower and lower. And the same is true when we go down group 7A. Some properties of ionic compounds. Well, ionic compounds are hard, they're rigid and brittle, and they have high melting points, very high melting points. In the solid form, they do not conduct electricity, and that might be sort of, you might not really think that because they are charged particles, you might think they would conduct electricity, but in the solid form they don't. The ions are fixed in place, so there's nothing to transfer charge. Ionic compounds do conduct electricity, though, when they're melted or when they're dissolved, such as dissolving in water. In these cases, the ions are free to move, and they can carry a current. Figure 9.9 in your book shows why ionic compounds crack. So if you imagine smashing a big piece of salt with a hammer, or a lot of minerals and rocks, same thing. At a microscopic level, when you hit this crystal with a hammer, what are you doing? Well, you're moving it, and when you move it to where there's two positively charged ions next to each other and two negatively charged ions next to each other, what does that do? They start repelling one another, and that's where the crack forms. Now, when we look at conductance, if we put a light bulb into a thing of just ordinary solid salt, we see that the light bulb does not turn on. The current cannot pass through the solid salt because the ions are immobile. When we dissolve it in water, the ions now can travel, they can carry a current, and the light bulb will light up. And the same thing would happen if you were to heat this salt and melt it into a liquid. What happens when an ionic compound vaporizes? Remember, ionic compounds have very high boiling points. And that's because the interaction between the two, the positive charge and the negative charge, is very strong. And this interaction is so strong that when it is indeed heated enough to boil, what you get is an ion pair that boils off. You can't really separate the two charges ever. And moving on to covalent bonding. Visit this figure again, slightly different than the one we saw before, figure 9.12 in your book. Remember, we have at point 1, we have two hydrogen atoms that are far enough apart where they don't really know the other one exists. The potential energy there is 0. As they get closer, the electron cloud from one is feeling the nuclear attraction from the other. There comes a certain point where they reach an optimal distance apart from one another. And if they get any closer than this, the nuclei start repelling one another. And this minimum, the depth, again, of this minimum is the bond energy. And so this energy is absorbed when the bond breaks. So it would need, in this case, 432 kilojoules per mole to break that bond. But when the bond forms, that much energy is released. So when two hydrogen atoms come together, they actually release 432 kilojoules of energy per mole. Your book likes to show these electron density figures. And I think this part is a pretty good figure to tell you why the bond length is what it is. You have these forces. You have attractive forces between the nuclei and the electrons. But you also have repulsive forces between electron and electron and between nuclei and nuclei. So it's really a balancing act with these attraction and repulsion forces. And we can give a picture of a bond like this with an electron density map, where there's a great deal of density near the nuclei, but also between them. And this is really key, this saddle. The higher that saddle is, the more electron density there is between the two nuclei. And that tells you that there is indeed a bond forming between those two nuclei. Atoms share electrons to achieve a full outer level of electrons, like we've discussed before. The shared electrons are called, not surprisingly, a shared pair. You can also call them a bonding pair. And you can represent shared pairs as a pair of dots, like in this Lewis symbol, or probably more commonly, it's shown as a line. So two electrons become a line. And this is now, it's not a Lewis symbol anymore, it's actually a Lewis structure, which we'll be talking about in chapter 10. So an outer level electron pair, such as some of these in fluorine, they're not involved in bonding. So we call these lone pairs or unshared pairs, but more commonly we call these lone pairs. So a pretty important concept in covalent bonding is bond order. And what bond order is the number of electron pairs shared by a given pair of atoms. So if you have a single bond, that's a bond between two atoms, and it has one pair of electrons that are being shared. We call this a bond order of 1. Now, bond energy is the energy needed to overcome the attraction between the nuclei and the shared electrons. And if you remember our potential energy plot, the bond energy is how deep that plot is. Now, the stronger the bond, the higher this bond energy is, or the deeper that figure, that plot would be, that potential energy curve would be much deeper for a stronger bond. And bond length is the distance between the nuclei of the bonded atoms. So let's look at some trends with bond order, energy, and length. For a given pair of atoms, a higher bond order results in a shorter bond length and a higher bond energy. So bond order and bond energy follow the same trend. Bond length is the opposite. For a given pair of atoms, a shorter bond is a stronger bond. And when we look at the periodic table, bond length increases going down a group in the periodic table. So what does that mean? Bond length is increasing, bond strength is decreasing, going down a group. And when we go across a period from left to right, bond length decreases. So that means bond strength increases when we go across a period. Let's look at the halogens. Group 17, or the old nomenclature would be group 7A. So for fluorine, the top of the group, the bond, the intermolecular distance, or internuclear distance, I should say, bond length would be 143 picometers. Now when we move one element down in that group to chlorine, in Cl2, now that internuclear distance has increased to 199 picometers. And we can see this trend continue with bromine, up to 228 picometers, and iodine, it's up to 266. So as we go down a group in the periodic table, bond length is getting larger and larger. And conversely, bond strength is getting smaller and smaller. Table 9.2 gives you some average bond energies. It's a pretty large table. There's lot going on here. I pointed out because you might, in certain homework problems, certain problem set problems, you might need to refer to this table to find a bond energy. I'm going to highlight one section of this table that's highlighted in table 9.3, and that's this trend with bond order. So if we look at the first three molecules in this table, they're all carbon-oxygen molecules. The only thing different between them is the bond order. The first one is a single bond, so the bond order is 1. The length is 143 picometers, and we see here the bond energy is 358 kilojoules per mole. Now when we increase bond order, so we go to 2, a bond order of 2, that means it's a double bond. The bond length goes down, and the bond strength goes up. And again, bond order of 3, length goes down even further, and the strength goes up even more. Let's try another practice question. This time use the periodic table, but not tables 9.2 or 9.3, and try to rank these bonds in each set in order of decreasing bond length and decreasing bond strength. And here's a general plan for you to follow. So for part A, atomic size increases going down a group. So if we put these in order of atomic size, this is the order we would come up with. So what does that mean? So the bond length, the largest atom here would be selenium. So our bond length, the longest bond would be nitrogen selenium, followed by nitrogen sulfur, and the shortest would be nitrogen oxygen bond. And the bond strength, well, that's just the reverse of the top trend. The shortest bond is the strongest bond, and the longest bond is the weakest bond. Okay, let's move on to B. By ranking the bond orders, we would get carbon oxygens, the longest bond, carbon double bond oxygens next, and carbon triple bond oxygen is the shortest. And again, the bond strength is the opposite of that trend. And finally, part C, atomic size decreases when we go from left to right across the periodic table. So nitrogen is the biggest, oxygen is the next biggest, and fluorine is the smallest. What does that mean for bond length? The carbon-nitrogen bond is going to be the longest, carbon-fluorine bond the shortest, and again, the bond strength trend is the reverse of the bond length trend. Figure 9.16 in your book gives examples of covalent bond networks. So ionic compounds can make solids. Covalent compounds can also make solids. And here we see quartz and diamond. And these bonding networks can be very long and very extensive and actually lead to compounds that are even stronger than ionic solids. Figure 9.15, it gives a very good explanation of why covalent compounds can boil. And that is, in the liquid phase, you can have very weak forces between molecules. And these forces can easily be overcome, and the molecules can be vaporized. But if you notice the molecules, the covalent molecules themselves, those forces are very strong and they don't break easily. So the molecules hold together. And we won't get a chance to talk about intermolecular forces in this class. It's just not long enough, but they are very important. So I like to bring them up, but we really won't have much time to talk about them in any detail. Okay, we're skipping chapter 9.4. There's a little bit too much material that we're going to not cover until we talk about chapter 6, so we're going to have to skip that. But moving on to 9.5. A covalent bond, which shared electron pair, is not shared equally, but remains closer to one atom than the other. That's called a polar covalent bond. The ability of an atom in a covalent bond to attract the shared pair is called electronegativity, and this is an important term. Unequal sharing of electrons causes the more electronegative atom of the bond to be partially negative, and the less electronegative atom to be partially positive. And we can indicate this polarity by drawing an arrow with a plus at one side to represent the positive side. And a classic example of a polar covalent compound would be HCl. So we talked about the flavors of bonding, and if you want to think of a covalent bond as chocolate and an ionic bond as vanilla, it turns out that there's really many compounds that are sort of a mix between the two. They're kind of like a swirl flavor. And here we see what a pure covalent compound, Cl2, the atoms are both the same. And we see that they share the electron. This electron cloud is shared evenly between the two. The bottom example is a pure ionic compound, sodium chloride, where we have a complete transfer of electrons. So we have a sodium cation and a chlorine anion. There's no sharing of electrons. But somewhere in that gray area between the two, we have HCl. There's sharing of electrons, but chlorine takes most of a little bit more of the electrons. So the electrons spend a little bit more of their time next to the chlorine atom as opposed to the hydrogen atom. And this would be considered polar covalent. Again, you can use that little arrow to tell you which side is positive, partially positively charged, and which side is partially negatively charged. And this whole idea of electronegativity, this came from Linus Pauling. And again, electronegativity, it's the ability of an atom to attract bonding electrons. And the periodic trend, as you might expect, is very similar to ionization energy and to electron affinity. And that is, when we go across a group or up a group, electronegativity increases. So the nonmetals are more electronegative than the metals. And electronegativity, when we talk about electronegativity, we don't really consider noble gases because they don't form bonds. The most electronegative element is fluorine. In general, again, electronegativity decreases as you go down a group as atomic size is increasing. And it increases across a row as atomic size decreases. And nonmetals are much more electronegative than metals. If we look at the trend compared to ionization energies, we see that the basic trend is the same. But when we look at the purple ionization energy, we see there's some exceptions, right? You have these step downs. Remember, and that's because you have it's much easier to remove one p electron than one of the filled s shell electrons. And it's easier to remove the fourth p electron to get to a half-filled p orbital. So that's you get these exceptions to the rules for ionization energy, but you don't get that for electronegativity. If you follow the blue, it's as you go across the row, every step of the way, you're increasing electronegativity every time. Here's a figure that shows electronegativity with respect to atomic size, and you can see that trend, it follows that trend really, really closely. The bigger an atom is, the less electronegative it is. The smaller an atom is, the more electronegative it is. Now, the polarity of a bond, that is how unequally the electrons are shared, that increases as the change in electronegativity of the two atoms in that bond increase. Now, when we look at the group 7A, the halogens, when they form bonds with hydrogen, fluorine is the most electronegative atom, the most electronegative element. When it forms a bond with hydrogen, the change in electronegativity between hydrogen and fluorine is 1.9. And you can see the electron, they're not shared evenly at all. A very polar bond. As we move across this chart, so as we're going down the halogen group in the periodic table, next we go to chlorine, the delta En is 0.9. Now you see, again, the electrons aren't shared evenly, but there's less of a discrepancy compared with HF. HBr is a 0.7 difference between the two electronegativities. And finally, HI is 0.4. And again, this is the least polar bond. The electrons are being shared the most in the HI bond compared with the others. Now we can look at delta En ranges, values, to help classify what type of bond we have. And this is the figure from your book. So these are the values that we will use in this class when we want to classify a character of a bond. So from delta En of 3.3 to 1.7, that is going to be considered an ionic bond. From 1.7 to 0.4, we're going to consider those polar covalent. 0.4 to 0 would be mostly covalent. I would be fine if you use the term just covalent. And then the only true non-polar covalent bond would be when the delta En is 0. And most commonly that's going to occur when you have two of the same atom bonding together. And we can also remind ourselves that when we're up in this region, the ionic region, where we really do have an electron transfer, we have a cation and an anion. When we're in the polar covalent region now, we have a situation where there's uneven sharing. So we have what's known as a dipole, which is shown by this arrow, the plus being on the positively charged side and the arrow pointing towards the negatively charged side. Figure 9.25 shows the percent ionic character as a function of the difference of an electronegativity. Not much really surprising here when we have compounds like chlorine, for example, has a delta En of 0. Its percent ionic character is 0. It's not ionic at all. But when we have metal and non-metal bound up here, we see that the delta En is much higher, and the percent ionic character of those bonds is, again, much higher. I remember when we were talking about covalent bonds, we showed an electron distribution plot. If you remember for I believe it was H2, we saw that the saddle was really high, indicating that there was a great deal of electron sharing between the two nuclei. In this case, the saddle's much lower, but there is a little bit of overlap between the two, and that indicates that there is really some electron sharing occurring, even in a compound like lithium fluoride. Okay, practice question 3. Which of the following bonds in each pair are the most polar? I've included the chart of electronegativities so you can have a reference, but hopefully you'd be able to answer a question like this on a test without knowing the electronegativities. So if we look at the first choice, carbon-sulfur or carbon-oxygen. Well, carbon and sulfur have the same electronegativities, so they're not going to be polar at all. Oxygen is much more electronegative than carbon, so that's going to form the more polar bond. But we could, without given those values, we could choose CO over CS because oxygen is higher in the group than sulfur, so it has a higher electronegativity than sulfur. Part 2 is a trick. Chlorine-chlorine and oxygen-oxygen, those are both going to be non-polar, so neither of those. And finally, nitrogen-hydrogen bond or carbon-hydrogen. Even if we didn't look at these values, we know that nitrogen is further towards the right in that row of the periodic table, so it is going to have a higher electronegativity. Therefore, it will be a more polar bond when it bonds with hydrogen. Let's try a question now where we have to identify the type of bond. And then, out of our 4 choices, which is the most polar? So for carbon, bromine, and this is where, for a question like this, you would need to have the electronegativity values. If you're trying to classify a bond as ionic, polar covalent, mostly covalent, you would really need the electronegativities. So I'm going to give the delta En values. Carbon is 2.5, bromine is 2.8, so the change of electronegativity between the two would be 0.3. And what would that be? That would be in this region, mostly covalent. Oxygen and hydrogen, 3.5 minus 2.1 gives a delta En of 1.4, and that lies in the polar covalent region. Now HF, we have 4 minus 2.1, that gives 1.9, and that is now in the mostly ionic region. And finally, carbon-fluorine, we have 4 minus 2.5, which is 1.5. Again, that's in the polar covalent region. And the strongest, or excuse me, the most polar bond here would be between hydrogen and fluorine, the delta En of 1.9. It's basically an ionic bond. So an important concept with electronegativity is oxidation number. Now, oxidation numbers, they're used to describe the electronic environment around atoms in a molecule. And electronegativities are needed to assign oxidation numbers. Now, why is that? It's because the more electronegative atom is assigned all of the shared electrons. And the less electronegative atom in a pair is assigned none of the shared electrons. Each atom in a bond is assigned all of its unshared electrons, so all of its lone pairs. And you can calculate oxidation number given this equation. So oxidation number equals the number of valence electron that free atom would have minus the quantity of shared electrons plus unshared electrons. Let's look at an example. Let's use HCl. Chlorine is more electronegative than hydrogen. So for chlorine, we'll assign all the shared electrons, the two, in this case we have two shared electrons. We're going to assign those all to chlorine. Now, when we calculate the oxidation number, chlorine has 7 valence electrons. The shared electrons in this molecule are 2, and the unshared electrons on the chlorine are 1, 2, 3, 4, 5, 6. So oxidation number becomes 7 minus 8, which would be a -1. Now hydrogen is less electronegative than chlorine, so it doesn't get any of the shared electrons, and it doesn't have any lone pair or non-bonding electrons. So its oxidation number is 1 minus 0, or a +1. Now we've talked a little bit about this, but here are some ways to depict polar bonds. And one is using the dipole arrow. The head of the arrow points to the more electronegative element, and the plus side end of the arrow is towards the positively charged, or the least electronegative element. And you can always also show a polar bond using these lowercase delta plus and delta minus. What that means is that there is a partial charge. It's not a full charge. This isn't an ionic bond or an ionic compound. These are only partially positive or partially negative charges. Okay, let's try a final practice question here. Calculate the oxidation numbers for each atom in the following bonds. So for number 1, nitrogen and hydrogen. So what's the oxidation number for nitrogen? Nitrogen normally has 5 valence electrons. We're going to have to show some lone pairs here. So we have which element is more electronegative? Nitrogen's more electronegative, so it's going to get assigned both shared electrons. And it has 4 lone pairs. So the oxidation number of nitrogen is going to be a -1. Now for hydrogen, it normally has 1 valence electron. It doesn't get any of the shared electrons, and it has no lone pairs. So it's going to be a +1 oxidation number. And we can draw, if we wanted to draw a dipole, we would draw it like that. Okay, on to number 2. Oxygen. 3, 4. It helps to complete the Lewis symbol. So if we think about these as Lewis symbols, hydrogen has 1 electron, oxygen has 6. So oxygen would normally have 6 valence electrons. It's more electronegative than hydrogen, so it gets both shared. And we have 5 unshared or lone pair electrons on oxygen. So we get an oxidation number of -1. Now hydrogen, again, it's the same as for the NH bond. It's going to have a +1 oxidation number. Another thing you should notice here is that the oxidation numbers of all the atoms in a molecule, they add up to the formal charge on that molecule. So all of these molecules are uncharged, so the oxidation number should add up to be 0. So +1 -1 equals 0. So that should be the total charge on your atom, on your molecule. Now let's look at HF. So fluorine will have 7 valence electrons. It's going to get both shared electrons because it's the most electronegative in the pair. And it currently has 6 non-bonding pairs. So it will be an oxidation number of -1. The hydrogen, again, is going to be oxidation number of +1. And if we draw the dipole for this molecule, it'll be going in this direction. Now finally, we'll look at carbon-fluorine bond. So carbon normally has 4 valence electrons. It's going to get none of the shared pair, and it has 3 non-bonding electrons, so that equals a +1. And fluorine, again, we have 7 - 2 + 6, so that's going to be a -1. And figure 9.26, just to illustrate this point, how the more covalent a bond is, the more density you'll see between electron density you'll see between the two nuclei. We'll take chlorine and bond it to all the elements across the third period. So starting with a pure ionic compound like sodium chloride, you see that there's basically no density between the two, so there's no shared electrons. As we move across group 3, the amount of density between the two nuclei increases until we get a chlorine-chlorine bond, which would be a pure covalent bond. And we can see this, the same pattern, or the same group of atoms, but now we're looking at their appearance. So they go from sodium chloride, a hard, brittle solid, and that slowly turns into compounds that are liquid, and finally with the chlorine, which is a gas. And the properties of these, as the difference in electronegativity decreases, the melting point decreases, the electrical conductivity decreases, because the bond type is changing. It's changing from ionic to polar covalent to non-polar covalent. So this change in bond type is reflected in the physical and chemical properties of these compounds. And now we'll kind of work into a little bit of an aside. It's a special section in the book talking about infrared spectroscopy. And I think this is really important to point out. mainly because we talk about bonds when we draw Lewis symbols, Lewis structures. We sort of picture them as being rigid, but bonds are not rigid. They actually have motion in them. And the specifics of these motions are not important. I just want you to realize that they have motions, these molecules, and they can have something what's called a symmetric stretch, and we see here with CO2. And we show the partial charges because oxygen is more electronegative than carbon. Can have an asymmetric stretch where the two bonds are going in the same direction. And then there's a bending mode. They can bend in and out of the plane for this linear molecule. So what's the big deal? How can covalent bond motions be used to gain information about a molecule? And the answer to that is using infrared spectroscopy. Like electronic states that we saw in Chapter 7, energy levels of vibrations in bonds are also quantized. So molecules can absorb infrared radiation to move up to a higher vibrational energy level. And this is similar to how molecules can absorb visible or ultraviolet light to move up to a higher electronic energy level. And if you remember the picture of an absorption spectroscopy, where you have a light source that you shine through your sample. Now, if you use a light source that gives off infrared light, you get what's known as an infrared spectrum. And these, I wouldn't expect you to know this. This is something that you might have to learn in organic chemistry, and definitely in organic chemistry lab. I think you would do something with IR spectroscopy. But this is just to illustrate the different types of bonds you can see using infrared spectroscopy. They all have sort of a unique absorption wavelength. And it's really an important tool to characterize. If you have an unknown compound, you can tell really just what kind of bonds are in that compound and help build the structure of that unknown compound. Here's an example of just how powerful this can be. If we have two molecules that have the same exact atoms in each molecule, they're just bonded a little bit differently. And you can actually tell the difference between the two by using IR spectroscopy. They give different spectra, even though they have the same molecular weight, the same exact atoms in each molecule. Here's another example of that. We have very similar molecules. The difference in them is the position of this methyl group. And you see, again, they give different IR spectra. So bonds can be pieced together by infrared spectroscopy. And that's good news if you're a chemist and care about that sort of thing. But what about for the people who aren't chemists, who don't care about that? Why are bonds important? Well, one example is when the sun shines on the Earth. The sun gives off many different frequencies, but a lot of the light from the sun that hits the Earth is actually in the IR region of the spectrum. And we feel this as heat. So that normally comes into the Earth's atmosphere hits the Earth's surface, but then it gets reflected. A lot of this heat, IR radiation, gets reflected back into space. But if we have too many molecules in the atmosphere that now absorb that IR radiation, that infrared light, and don't let it be reflected back into space, the temperature that is usually pretty constant at the surface of the Earth, what that does is now it rises and it gets hotter and hotter, and this is what's known as the greenhouse effect. So it's really important to have an understanding of chemical bonds. They're even very simple chemicals like CO2 are very important on a global scale for everyone. All right, we're going to continue on to chapter 9.6. This will just take a couple minutes. It wasn't on your reading assignment. I just want to include it really quick for completeness. So as we talked about, the third flavor of bonding is metallic bonding, and this is an electron C swimming amongst a cation. So all metal atoms in the sample contribute their valence electrons to form a delocalized electron, what we call C. And these metal ions, the nuclei with the core electrons, lie in an orderly pattern within this mobile electron C. All the atoms in the sample share electrons. And the metal is held together by the attraction between the metal cations and the sea of negative valence electrons. So what are some properties of metal? Well, metals are generally solid. There's a few examples, such as mercury, where they can be liquid, but generally they're solid. They have fairly high melting points, not as high as ionic compounds, though. But they have much higher boiling points. So if you're curious, the melting point will decrease down a group and increase across a period. Metals can be shaped without breaking, unlike ionic compounds. This is because the electron C allows the metal ions to slide past each other. Metals are good conductors of electricity and of heat. But they conduct electricity both in the solid and liquid state. And this is because the electron C is mobile in both phases. And like I just said, the metals are really good conductors of heat as well as electricity. So here we see some melting points of metals. And you notice that the boiling points are much, much higher than their melting points. And as we go across the periodic table from left to right, the boiling point and melting points increase. And as you go down a group, the melting point increases. And compare this with the melting point and boiling points of some ionic compounds. Ionic compounds tend to have slightly higher, I would say, on average melting points, but lower boiling points than metals. And I just point out really quick, you notice that magnesium oxide has really high melting point, really high boiling point. Why is that? What makes it special compared to some of these others? Well, that's because magnesium is a 2+ ion and oxygen is a 2- anion. So if you remember Coulomb's law, that makes that bond charge A times charge B divided by the distance. If the distance is roughly the same as some of these other ionic compounds, that would make the bond strength roughly 4 times as strong as singly charged ions. Here we see melting points of group 1A and group 2A metals. You can see as you move down the group, the melting points are decreasing for the most part. You also notice that group 2A has a much higher melting point than group 1A. And why do metals bend instead of crack? Well, when you hit them with an outside force, they can deform because the lattice can move because that electron C is mobile. Okay, next class, next Friday, I should say, we're going to have the first exam, and it's going to cover information from the first day of class and the 3 online lectures that you should have viewed. So that's Chapter 7, Chapter 8, and Chapter 9. And then starting next week, we're going to move on to Chapter 10, talking about Lewis structures and molecular shapes.